Thank you for our introduction, Dr. Orange and Mimic. And good morning, everyone. Thanks for coming. And thank you for having me here. It's a pretty good campus. Just like Dr. Orange and Mimic said, today I'm going to present my research on memory system design with emerging technologies. Before we get to the main topic today, let me briefly overview my research interest. My research spans in 3 areas: computer architecture, electronic design automation, and VLSI design. And my past work is largely driven by the properties of new circuit and device technologies and the requirements of modern applications. I have been working on several different things, many different things actually, but today I'm not going to talk about all of them, but focus on memory architecture design for in-memory applications with one of the emerging technologies called NVRAMs. And here, examples of in-memory applications are in-memory databases and file systems. These applications need to store all or most of their data in the main memory. And this data can be gigabyte, terabyte, or even larger in size. So this huge amount of data can face significant challenge for memory system design. So I would like to discuss how to re-architect the memory system to achieve efficient and reliable data movement. The memory is a critical component of all computing systems, whether they are servers, personal computers, or mobile. The memory serves as a bridge between the processors via caches and the storage system like flash and disks. For decades, our computer system adopted a 2-level storage model with fast, volatile memory updated by loads and stores, but data lost when system halts or reboot. And slow, non-volatile device managed by storage systems like databases and file systems, while data can survive across system boots. But this traditional storage model may be changed by the new memory technology called byte-addressable non-volatile memories, or NVRAMs. There are various types of NVRAMs. We call them phase-change memory, resistive memory, or memristor, or spin transfer torque memory. These memories are implemented with different physical devices. They have different cells, but they share some common properties, just like their name indicates. They are byte-addressable, like a memory, and also non-volatile. NVRAMs have been extensively studied in both academia and industry. For example, Intel is starting the programming model to accommodate this new memory technology. And OS vendors like Microsoft and Red Hat, actually, a couple of weeks ago, I was in SNIA Summit on NVRAM. So a lot of industry companies attend that workshop talking about how to program the system and how to provide device for this new memory technology. So in that summit, actually Microsoft and Red Hat are talking about how to adapt OS kernel and the file system with this new memory technologies. And also memory vendors like Samsung, SK Hynix, and Micron, every year they demonstrate their new implementation of this memory technology. If we only compare NVRAMs with either memory or storage technologies, we can find that they are a little bit low. Hope you can see it. They are as fast as SRAM. This is the memory technology used in caches. And also as dense as DRAM, this memory technology in the memory. And also they're non-volatile, so they're like the storage devices. So people have been working on to study how to replace them in the cache or the memory or the storage system. However, if we put NVRAMs together with memory and storage, we can find that they have both memory and storage properties, being byte-addressable, fast like memory, and also non-volatile like storage. As a result, MRAMs can potentially change the traditional way of memory and storage organization by blurring the boundary between the two. So in the rest of this presentation, I would like to discuss what new design opportunities MRAMs bring in and how to optimize the designs. In particular, I would like to first talk about memory's interaction with storage, which lead to persistent memory design, and then talk about memory's interaction with caches. So let's start from the first one, the persistent memory design. If I search persistent memory over the web, the most results I got on the first page is actually a famous painting by a Spanish artist or a novel published in 2004. Actually, this is what I got yesterday. Last night I was searching. But of course, today I'm not going to talk about either a painting or a novel. Today I'm going to talk about the term persistent memory in computer engineering. As recall that our computer system adopted a two-level storage model with separated memory and storage. And the memory is designed for fast data access. The storage is designed as the permanent home of data. That means that the data do not get lost or corrupted during system crash or power loss. And we call this property as persistence. However, when MRAM comes into the picture, things start to change. As we have seen, MRAM has both memory and storage properties. So it can bring in a new design opportunity actually called persistent memory. So it is the memory but also persistent. Persistent memory has been a dream of in-memory applications designers for a long time because it allows application data to access the persistent data through a memory interface with load and stores without the need to page data in and out the disk or flash. It actually can improve the system performance by a great deal compared with using storage devices, as demonstrated by several recent studies. These previous persistent memory designs and these studies can improve the system performance by a great deal compared with storage and storage devices. However, if we compare to a memory system, their performance is still poor. What we find is that traditional memory system design can achieve high performance, but unfortunately, they do not guarantee any persistence. So the goal of our work is to provide both persistence and high performance in memory. In particular, we study how to provide persistence in memory and then investigate their impact on system performance. And finally, we design a hardware-based persistent memory design to optimize system performance. So let's first start from the first step to study how to provide persistence in memory. As in traditional system, persistence is only supported in a storage system. So to understand how to provide persistence in memory, we need to first study how persistence is supported in a database or file system. A database and a file system is updated by transactions. And a transaction can contain multiple write requests. And the database and file system need to maintain ACID properties to guarantee that transactions are processed reliably. So just like storage system, persistent memory also need to maintain these properties. In particular, in our design, this durability property is naturally satisfied by the non-volatility property of MRAMs. And we support isolation properties between different threads by using existing concurrency control mechanisms. So mutexes, semaphores, and transactional memories are also examples of concurrency control mechanisms. Maintaining atomicity and consistency is the main source of performance overhead in persistent memory design. So we'll take a closer look at them. In particular, the atomicity properties requires that a transaction is all or nothing. So that means either a transaction is completely executed, completed, or failed completely. Because a system can crash while a transaction is updating to multiple data blocks. So without this atomicity, data can be corrupted by a partially completed transaction. A common method to maintain atomicity is multi-versioning. Most previous persistent memory design borrow mechanisms from databases and file systems to maintain multiple versions of data. And the idea is pretty straightforward. Say we want to maintain multiple versions of data, we can actually allocate at least two separate memory regions for the two data copies. One of them, for example, store the original data, and the other of them can store a log or a temporary data buffer. So a transaction can update to one of the versions at a time, but not updating to two versions at the same time. So in this case, the updates do not, for example, do not override the original data directly. Then the system can crash in the middle of this transaction. But even though one of the version is corrupted by this partially completed transaction while the system crashes, the original data will always intact because it is not updating at this time. So it is always valid. So we can always undo this transaction with this valid version of data and pretend that the transaction has never been executed. Sure.
Yeah, how does the inclusion of NVRAM change this? Because I mean, this is already done by, as you mentioned, the database systems, right? They have to do the multi-versioning to make sure the asset properties. How does NVRAM change that?
So your question is that if my main memory becomes non-volatile, then how does things change?
Yeah, whether it's a non-volatile versus DRAM, how does it change the operation?
Okay, so this is actually evaluated in previous work. They find out 32x performance improvement. That performance improvement actually comes from because NVRAM, your memory is DRAM, you have to page data in and out.
Sure,
you have
right.
to do checkpointing.
So the performance impact, I don't understand. But the operation-wise, those are identical, are they? Or are there any differences between the operations that the software is going to do? Time-wise, delay-wise, I can definitely see NVRAM helping tremendously. Because you don't go to the disk, milliseconds, right?
So your question is, if it is DRAM, then is there anything different than it is NVRAM?
Yes.
So actually, if it is DRAM, we don't need to do this multi-versioning in memory, because multi-versioning is actually doing storage system. In DRAM, we have a data address overwrite it. Then system, if it crashed, then all the data is gone. So the data in your storage is good, because you're doing multi-version there. But your DRAM is all the data is gone, so if it is inconsistent or anything, when your system comes up again, you need to reload this data back to the memory. So your data is still good, yeah.
So I think the question is, so in a database system that operates on a disk, you use locking and logging, and in some cases versioning or optimistic locks to achieve the asset properties. What's different when you replace the disk with an NVRAM? I mean, does that functionality in a database have to change? Is there something fundamentally different in how you achieve ACID in NVRAM versus ACID over a disk?
So your question is if now I have NVRAM instead of disk, functionality, is it changed?
No,
so
I mean, I'm writing the database system, right? So I use I don't know, redo logging. I'm Oracle. I use redo logging plus undo logging. I use optimistic locking, and I rely on the disk for durability. So now I rely on the NVRAM for durability. What else do I have to change?
So this is how previous work do. I'm on the page of previous work. So they actually, as I said, they borrow the mechanism from database and file system. So actually, they perform their behavior is similar to the database and file system. So it's not that different. So my work is when can we make different if it's NVRAM? So we'll see later. hopefully I can answer your question later. So this how previous work do to the persistent memory. But actually, if we think about it, it brings in performance overhead, because now if we need to update one data, we need to do 2 writes to the memory. And actually, we find that it's increase the memory traffic by a great deal. Memory is for fast data access. If you increase the memory traffic and introduce this performance overhead, it does not make sense, in fact. And another property is consistency properties. So it is important for persistent memory design, because without the ordering control, the persistent memory may risk data corruption. For example, we have 2 transactions updating a data and a metadata referenced to it. The software will be programmed in a way that the 2 transactions are issued in order. But before all the writes arrive at the persistent memory, they need to travel across the cache and get queued in the memory controller. Those part of hardware components, they will try their best to optimize the system performance by reordering those writes. So without ordering control, the later issued transaction may arrive at the persistent memory and commit before an earlier issued transaction. If system crashed before the earlier issued transaction is completed, then your metadata will reference to partial updated and meaningless data. So we need to perform ordering control. And previous work, how they perform ordering control, again, something sort of like the database and file system. They restrict the ordering of writes arriving in memory by insert cache flush instructions between transactions. So transaction 1, then cache flush, transaction 2, cache flush again. So they flush the cache blocks through the cache hierarchy all the way down to the memory. So this actually can ensure ordering control, but it is another source of performance overhead, because all those hardware components performance improvement optimization is actually canceled out. So this is how previous persistent memory designs do. They root from the database and file system mechanisms. They're pretty similar to those, but they incur performance overhead. We develop a comparison baseline we call native. This is provide no persistent support in memory, so it's like a DRAM system, but we just replace DRAM with NVRAM, but we do not ensure data correctness. So its performance is actually represent the ideal performance for persistent memory design. We need to make it as our performance goal. We need want our performance to be as close to that native system baseline. And we construct a set of benchmarks with data structures used in database and file systems, and perform inserts and deletes to these data structures. What we find is that when we evaluate the system throughput in terms of inserts and deletes, it turns out that previous persistent memory design result in performance degradation by a great deal. So now we have studied the source of performance overhead of previous persistent memory design. I'm going on to present how we optimize system performance with hardware support. Let's think about what can be leveraged from hardware. And my answer will be a different view of memory system. So as we have seen, most previous persistent memory design root from software perspective. And software's view of a memory system is a flat address space. So to maintain multiple versions of data, they need to explicitly divide this flat address space into multiple regions. But different from the software, hardware's view of a memory system is not flat, but a hierarchy. And in this hierarchy, it has multiple levels of cache and then the memory. So from hardware perspective, this hierarchy already have multiple regions. We do not need to explicitly divide it. So based on this observation, we are able to develop a multi-versioning mechanism with hardware support. Let's think about how does cache hierarchy work. If a processor wants to write a new value, it writes to the first level cache first. Then the old value remains in the lower levels. until the new value gets evicted to the next level. So before this new value is evicted out of last level cache, the old value will always remain in the main memory. So if we think about this, this is a multi-version system by nature. So by leveraging this caching scheme, we develop design a persistent memory hierarchy. So we try to give some sense what makes sense if it is NVRAM, not a storage system. So in this hierarchy, in addition to just the NVRAM, like previous persistent memory designs do, we include the last level cache to be non-volatile as well. So now we naturally have two versions. One of version is stored in the main memory as the clean data, and the other version is stored in the last level cache as the dirty cache blocks. These two versions are actually mapped exactly to the same address. So just like the native system, our design allows updates to directly override the original data without the need for logging a copy on write. So this is what we differ from database and file system. Hope that answers your question. Thanks. And as regard to the ordering control, we only enforce the ordering of writes when transaction commits, but allow hardware to optimize system performance by reordering the writes arriving at persistent memory. Take the previous example again. If two transactions are issued in order, we allow the hardware to reorder those writes arriving at the persistent memory that's the last level cache. But we marked each cache block as uncommitted. So this uncommitted state will change in order. So when the last instruction of an early issued transaction is executed, we perform a cache flush to flush the remaining cache block from the higher level cache to the last level cache. After that, all the writes of the previous issued transaction arrive at the last level cache. We change the state to be committed. And after this early issued transaction is committed, we can change the state of the later issued transaction. Note that the cache flush can be performed really fast, much faster than before for two reasons. One of that is that now we only need to flush the cache blocks from high level cache to the last level cache rather than it all the way down to the main memory. So the distance is shorter, obviously. And also we can leverage its high memory bandwidth in the cache hierarchy rather than this narrow bus in the memory. And the other, okay.
Do you assume a write-through cache for the higher level cache, level 1 cache here, or is it is it write back?
It's write back.
It's write back, even the first level cache.
Yeah. First level cache can be write through.
It's the highest level.
Yeah.
I see. So
we have three levels: level 1, level 2. Level 1 can be write through, then 2
right,
and 3.
Yeah.
So this is the first reason. Then the second reason is that because the high-level caches are typically in small capacity, so actually what we find is that when a transaction commits, actually most of its cache blocks already evict out to the last level cache. So we only need to perform a really lightweight flush to in a high-level cache really fast. So now we have more on the hardware side. Let's move to visit the software. Oh, you have a question?
No, go ahead.
So,
previous slide?
Yes. So, typically you put things in the cache when there is any reuse. Do you see any reuse for these blocks there?
Could you rephrase?
Typically somebody will put data in the cache to take advantage of reuse. Do you see any reuse for the blocks that you have in your cache?
I still cannot quite get your question. Could you repeat? Sorry.
So the reason why a system will cache data is to be able to take advantage of reuse of this data.
Yeah.
For the blocks that you put into the cache system, does the system reuse them?
Okay, so you're talking about
before you flash them out.
So you're asking about, do I see reuse in my this design or my applications?
Specifically for the data blocks that you're using to maintain persistent.
I would say it depends on different applications. So for some of applications, we see reuse. Some of them we didn't.
So do you have any, will you show us any data later on this?
Here I don't have, but
Okay.
maybe offline I can like show
So
you my
for the
experience.
cases where there is no reuse, why don't you use uncached accesses?
Okay, yeah. So in our work, we cannot fit all the things in this. You provide a pretty good suggestion actually. So this is the actually first ever work we have seen to at least internal knowledge that it's hardware based. So this is our first step to evaluate how much performance we can gain by this kind of design by leveraging caching. But later we have like multiple steps of evaluation. You will see my future work slides. So we'll study like whether this design can be optimized in some way or tuned in some way, or other part. Actually, we're identifying this part of memory controller may be another performance bottleneck. So we will kind of have a tier for future work extending on top of this work. So you provide a pretty good suggestion. I will like considering it in my future work. But this work we didn't consider about that. Yeah, you're right. If it is cache is all about reuse. If it is not reused, it does not make sense. Then we have to like maybe need some software. I'm thinking about through it. Maybe we need some software interface to like hint whether this data is reused. Then we kind of distinguish between different applications or different phases in the same application to like do whether cache this data or flush another part of data. Maybe that part. Is it good? Thanks. Okay. So this is let's see what changed in our software interface. So here shows a piece of software code with single transaction in a loop. In previous persistent memory design, we can see that in addition to update your original data, we will need to call logging functions and cache flush instructions. But differently, in our work, we only need to perform update directly override the original data. So we have completed almost most part of our design. Let's revisit paths we have gone through. We start from a native system with no persistent support in memory. To install persistent support in a memory, previous persistent memory design incurred all this performance overhead to maintain multi-versioning and ordering control. And we leverage hardware support for persistent optimizations. And if we compare our design with the native system, we can see that the behavior now is pretty close. It seems that our hardware-based persistent memory design is in a pretty good shape now. But if we take a closer look at it, we can still see several implementation challenges we need to address. For example, only adopt the two-level last level cache and main memory persistent memory hierarchy does not necessarily secure multi-versioning. So let's quickly take a look at this example. Traditional cache hierarchy design has no knowledge about persistence, so it allows last level cache blocks to be evicted out at any time, even before a transaction is committed. So in this case, if we think about it, the two versions are actually being updated at the same time. It violates the optomicity property. If system crash in the middle, both versions are corrupted. So to address this issue, we develop a barrier between the last level cache and the memory. So before the transaction is committed, we do not allow the cache last level blocks to be evicted to the memory. And until after this state is changed, we can remove this barrier. And after this time point, the last level cache blocks of this committed transaction can be evicted out at any time. We availed our complete persistent memory design with a simulator originally developed in HP Labs, and we significantly modified to implement our design. And as the configuration, this part represents our persistent memory design. And in principle, our persistent memory can adopt any NVRAM technologies just when they are byte addressable and non-volatile. we can even adopt a DRAM with a battery in the memory. But here in our evaluation, we use STT-RAM, spin transfer torque RAM, because currently it provides the best performance and endurance among other NVRAM technologies. And as we have seen, we adopt these benchmarks we constructed with various data structures. And here shows the key example of our design. Recall that the native performance represents the ideal performance of our persistent memory design. We compare our design with native system and persistent memory adopted logging. And our results show that we can effectively bring the performance back up and close the performance gap between the persistent memory design and the native system. We also evaluate the scalability of our design across a number of threads. So as we can see here, persistent memory with logging, when the number of threads increase, the performance gap between is increasing quickly as well. But our design can always perform very closely to the native system. We also evaluate dynamic power because our multi-versioning mechanism can reduce the memory traffic by a great deal. So we can improve the dynamic power of the system as well. So above is the story of our persistent memory design. This is a memory instruction interaction with storage. As we have seen in the beginning, memory has interaction with the processor via cache hierarchy as well. So I will go on to talk about my work on memory's interaction with the cache hierarchy, which lead to a hybrid cache design. Here shows a big picture of this work. Modern applications need to deal with a large amount of data, so we observe an increasing gap between the bandwidth demanded by applications and the memory bandwidth that can be provided by the memory hardware. So in the rest of the presentation, I will refer to these terms as DBW and PBW. And instead of directly improving the memory bandwidth, we tackle this problem by maximizing the provided bandwidth at the cache hierarchy to minimize the demanded bandwidth to the main memory. And our solution is a hybrid cache hierarchy design with various memory technologies, including NVRAMs. So as we have seen from hardware's perspective, the memory system has multiple levels. And typically, the lower the level, the larger the capacity. And we find that there's actually a relationship between the demanded and the provided bandwidth in a level. In particular, the higher the provided bandwidth at the level, the lower the demanded bandwidth to the next level. And we profile the various memory technologies across the whole range of cache capacities. So it's the bandwidth versus capacity. And here, the SRAM and EDRAM are the memory technology that use in traditional caches, and the other two memory technologies are NVRAMs. What we find that is, as we can see, obviously, the curves are crossed with each other at different capacity points. So observation to sum up is that no obvious winner over the whole range of the capacities. So based on this observation, we designed a hybrid cache hierarchy that provides a highest bandwidth over the capacity range. To design such a hybrid cache hierarchy, we need to answer two questions to determine the first memory technologies, then second capacity to be used at each of the level. To help you better understand the curves, here I show a concept view of the curves. And to make the figure clean, I only include the three memory technologies that provide a high bandwidth. So what we do is that at each of the, because the curves are crossed with each other, the shared cache still use, the private cache still use the SRAM. Our design starts from the shared caches. So at each of the level, we choose the memory technology that provide the high memory bandwidth. So as you can see, we choose different memory technologies for different levels of cache. And as a result, we got a cache hierarchy that provide high bandwidth over the whole capacity range, as showing this thick red line called hybrid memory provided bandwidth curve. So this is our basic hybrid cache hierarchy design. What we also find is that different applications have a variable bandwidth demand throughout its execution. So no single design fits all applications. So for example, and when it is initialization, it does not need that high bandwidth. Then later, the bandwidth demand will be increasing. So we reconfigure the cache hierarchy to accommodate this changing demanded bandwidth. We predict the bandwidth demand while an application is running, and we map this bandwidth demand to this hybrid provided bandwidth curve. And we tune the cache capacity based on this mapping. If we find that the required cache capacity is smaller than the original configuration, we turn off the portion of unused capacity. Sorry for the lower part. If you cannot see, we turn off those unused portion of cache capacity to save power. We evaluate our hybrid cache hierarchy design with a multi-core processor, and we evaluate various memory technologies in our shared cache hierarchy and various capacities. We also evaluate with benchmarks selected from both multi-threaded and multi-program workloads. And here show the key results of our design. Our baseline is the cache hierarchy use only SRAM-based SRAM memory technology, and it turns out that our design can effectively, with hybrid cache hierarchy design, can effectively improve the system throughput with both multi-threaded and multi-programmed applications. So in summary, I have presented two pieces of my past work on accelerating the performance of persistent memory and optimizing the memory bandwidth. Looking forward, I see promising research directions in both dimensions. For example, in the persistent memory design space, we have studied how to optimize the multi-versioning and ordering control with hardware support. But in addition to that, further investigation steps need to be performed. For example, various well-studied hardware components are not well-suited for persistent memory design, as what we find. We observe that there are potential performance bottleneck, for example, in memory controllers, cache coherence, and prefetchers. So I would like to identify these performance bottleneck and study the solution and optimization mechanisms for this hardware components. And furthermore, incorporated with both memory and storage properties, MRAMs are promising candidates for design uniform single-level store, completely merging the memory and the storage. But in order to accommodate that, we need the merging of two vastly different formats of interfaces, the virtual memory and the file system. And so we need to, in this case, we need to identify the performance bottleneck and avoid those performance bottleneck in translating data, locating data, and moving data in these different formats. Also, we have work on persistent memory design applied to a single computing node But we need to ultimately go beyond a single node to apply the persistent memory to distributed systems, for example, data centers. And in this case, we need to first investigate the scalability of all our solutions. Of course, there are also raised in other potential issues. If you're interested, we can talk about that offline. More broadly, I see many research opportunities in both the driven by both new technologies and modern applications. Current computers designs are well shaped by traditional technologies like CMOS and DRAMs and disks, but new technologies are emerging with unique properties that likely to open doors to novel computer design. NVRAMs, as we have seen, is one example. But other new technologies, some I have been working on, some I'm exploring currently, can also yield abundant challenges and opportunities in computer designs. So I would like to study their implication to the three areas I have been working on: computer architecture, electronic design automation, and VLSI design. On the application side, I would like to profile and model the behavior and requirements of various modern applications. Only on top of the fully understanding of application needs, we can build high-performance, energy-efficient, and reliable systems. This concludes my presentation, and I would like to, I know I have a long acknowledgement list. I would like to thank my PhD advisors and thesis committee members, mentors, and colleagues, and also the collaborators, friends, and colleagues in the three institutions I have been working with. And finally, I want to thank all of you for your attention. And if you have any further questions, please don't hesitate to ask. Thank you.
So you're second to the last slides. You have actually a new technology called the last one, on-chip VR. What's that?
On-chip VR is on-chip voltage regulator. I don't have the space to spell it out. It is voltage regulator. So regulator currently, the real product, it is off-chip. So it is big. You have a processor chip. You have a separate regulator chip. But there is new technology, a couple of years, maybe 2000 or sometime. They find that this regulator can be implemented really small and put it on chip. For example, integrating it in the processor. So it has a lot of benefits. For example, now you can have, because it is small, you can have a lot of maybe several or 5, 6 into the processor chips. You can divide this processor into multiple regions controlled by different voltage supply dynamically. So you can save power in this way. But actually, it also has some downsides. For example, the power transition or transfer efficiency of on-chip is much lower than off-chip. So for off-chip, the input power and output power, the transmission efficiency is something like 90%. But for on-chip ones, it is only 70 to 80. So actually, if you use on-chip, you lose waste a lot of energy. So it kind of trade-off between the power saving and the efficiency. I have worked on performing DVFS with on the 3D chip multiprocessor with this on-chip voltage regulator. But recently, when I talk to people kind of think about, if we do not have DVFS, is there any better solutions on this? So we're thinking about like a smart place and route and like current routing mechanisms on that as well.
Do the on-chip VRs equipment that you're familiar with incorporate inductors, or are they switch capacitors?
The inductors. But inductor is pretty small in
So you mentioned 3D stacking and photonics and the new technologies. Do you have any more concrete ideas on what you'd like to do with these technologies?
Okay, so of course we can talk about later more about that, but here I will talk about some of my basic ideas. So for 3D stacking, I work on memory stacking for GPU graphics memories. So for when we have 3D stacked memory on chip, we have wider bus. So we have more bandwidth, but also we have to tune it because the application is not always using this high bandwidth. So I kind of developed a reconfigurable memory interface to accommodate different applications requirements on this. This is published in both conference and journal papers. But the area I'm not explore a lot is thermal, because with 3D stacking, the dies are stacked close together. So currently, a challenge of using 3D to be in real products. What I see, I recently attended a 3D IC conference in San Francisco. What I see, and based on what talk to people, is that one is cost. What I already studied the cost model on 3D chip. The other is thermal. So also AMD recent their panels, their keynotes identified thermal is a big problem for 3D. So I want to evaluate what kind of architecture design and circuit design and EDA design that can tackle the thermal problem of 3D stacking. For photonics, I did not have much work on this, but I and a colleague in my research group in Penn State, we have developed a simulator to simulate multiple nodes with photonic interconnection. But I would like to design. Currently, I have been working on the big memory system. But if we go NVRAM, of course, NVRAM has higher density than DRAM. Currently, similar density as DRAM, but NVRAMs are potentially, if we look at ISSC conference or IEDM conference, we can see that memristor is the capacity growing really fast, actually. So it is promising that can provide high capacity, but DRAM currently is still a mainstream memory device. So if we use the DRAM, how to provide high capacity is one challenge. So I'm thinking about using photonic interconnect to build a memory network to provide this high capacity without much performance loss. I have other areas I want to explore. We can talk about more when we're meeting. So you have a question?
I don't know a lot about the NVRAMs and the non-volatile, but so for example, in DRAM, there's some non-negligible amount of resources that they dedicate for error correction. They have error correction circuitry and so on and so forth. SRAMs, again, they have this issue of soft faults. So in terms of that kind of, is there any reliability challenge? Is there anything that can throw off a non-volatile memory?
You may.
In terms of making mistakes, making errors, corrupting data for whatever reason. Can temperature cause it? Can something else cause it? Is there something that, the other memory technologies have some vulnerability for some reason? Event upsets and thermal leakage and other things. So in the non-volatile, is it completely bulletproof? Is there anything that can, in terms of reliability, causing errors, causing incorrectness? Is there anything?
So I'll try to answer your question. So for non-volatile NVRAMs, actually they have the reliability problem as well. And if you look at previous papers, I can forward some. They have they need ECC and other error correction mechanisms as well. the different like mechanism that lead to this reliability problem of NVRAM is they have endurance problem. So like flash endurance pretty poor. DRAM has much better endurance, but NVRAM is kind of in the middle. So it is better than flash, but worse than DRAM.
That's so many times you can write it. So
Yeah,
many
it will. But different NVRAMs actually perform differently in this case. STT-RAM, why I choose this in my evaluation of my first work, persistent memory work, because it does not have this such of endurance. Its endurance is pretty close to CMOS, to SRAM. So actually, people are not thinking about. Actually, ever Spain, a company has announced that they are going to ship the STT-RAM, DDR3 compatible STT-RAM as a DRAM replacement. But phase changer memory has severe endurance problem. Okay.
Yeah. So could you, so not to like kind of just do to make you do a tutorial right now on all the different types of non-volatile, but like can you talk a little bit? So you mentioned the durability of STT-RAM being much better than say PCM. So what are some of the if you were to kind of talk about some of the alternatives to what you used in your work? So you mentioned the benefits of durability. Are there other sort of advantages of like phase change memory versus STT-RAM or?
Okay, so you're asking about if I put different NVRAMs together, what kind of trade-offs?
Yeah.
Maybe in performance, endurance, and
just
other,
yeah.
like generally. So I don't have a big picture. Our group used to have this big picture of the tables that can compare different columns. I don't have it in this presentation, but I'll try to explain it. Maybe later in our meeting I can show that table. So first, performance. Now I'm going to compare three memory technologies: STT-RAM, phase changer memory, and memoristic, called RAM, resistive mem. So STT-RAM has sort of best performance, both reads and writes. RAM, I will say, in the middle. Phase changer memory will be in the 3, but according to different configuration in device, our group has NVRAM sync a tool that can evaluate different configuration at the circuit level. Actually, by different configuration, you can trade off the performance and the reliability and also other costs or something. It can make some difference. But in general, as I see in the demonstration of those memory vendors, I will see STT-RAM, RAM, then phase changer memory, this performance. Then endurance, STT-RAM does not have endurance problem. RAM is better than phase changer memory, but not as good as STT-RAM. Phase changer memory has severe endurance problem, but still better than flash. For performance, another thing is typically NVRAM has longer write latency than read latency, so it is asymmetric, not like DRAM is symmetric. And what else? And also cost. I was asked by people about cost because I work on cost model for 3D technology, but for NVRAM, I cannot say exactly currently because it is not mature as 3D technology. But why a lot of people talking about phase changer memory is because now phase changer memory is more close to production recent previous years. But I see STT-RAM is coming up maybe last year or something, I mentioned the Everspin company. And also RAM, I know in China and Taiwan, I cannot remember the company, they shipped the demos on RAM, but maybe RAM is a little bit less close to the market than phase changer memory.
What about energy per read write operation?
So energy, first leakage energy. It is leakage because NVRAM it is non-volatile. So for device itself, it does not have high leakage, but all the leakage come from the CMOS part, the sense amplifier or something, peripheral circuitry. So this part is same as the SRAM, but the cell is SRAM is all transistor, and DRAM is a capacitor. So those parts, the leakage, NVRAM is much better. But for dynamic energy, because NVRAM has longer latency, read-write latency, and especially write latency, so it has much higher dynamic energy, especially write energy, than DRAM and SRAM. That's why a lot of work actually, previous work actually studied how to replace NVRAM in the memory and in the cache to tackle the leakage, the energy problem and the reliability problem. But not a lot of work, as our work try to leverage this non-volatility property. Yeah.
In the first part of your talk,
okay.
when you were talking about how you would utilize the NVRAM to have persistent storage. So when a transaction happens, you're using the NVRAM cache to provide multi-version, right? But now what happens when your transaction is large enough that it affects one of the speculative blocks?
So you're talking about because my last level cache, the capacity and associativity is limited. So in our paper, I think I have maybe I have a backup slide, hopefully. Yeah, this. So because we do not allow uncommitted cache blocks to be evicted out. So if the transaction is very large, larger than the capacity, of course, it cannot fit. So we'll say this transaction will overflow. In this case, actually, we fall back to performing copy on write here. So we get rid of this part and fall back to sort of like previous mechanisms, but we do it in with copy on write rather than doing logging. So we will interrupt first. Hardware will monitor a transaction if it can make forward progress. If it find out it's stuck there, it will say that it overflowed. Then it interrupt the OS. Then the OS will allocate a copy here. If I have animation. A copy here, so it do copy on write in the memory. But actually, I would say our mechanism, this design, is suitable for small transactions. So if you have a large transaction, it does not make sense to like using this cache because it will frequently fall back to copy on write. But if you have small transaction that can fit in last level cache, our mechanism can provide really good performance.
It's not, I think, just a matter of fitting in the cache. It's a matter of not having a single conflict. As long, if you have four-way associative cache, as long as you have 5 blocks mapping on the same.
Yeah. So this monitor. So two limitations: capacity and associativity.
Right.
Yeah.
So is this an argument to have, if you implement something like this in the real world, is this an argument to severely increase the associativity of the last level cache that you use as the NVRAM to minimize the case of conflicts and kind of push the problem to be more capacity rather than conflict oriented?
In this work, we didn't consider this, but I think this is a pretty good angle as well.
But I mean, your LLCs typically have high associativity.
Yeah, we evaluate like 16, 32. We have our evaluation results in our paper. I encourage you to read about it. We have a paragraph. We have a paragraph talking about our benchmark, how much granularity lead to how much rate of overflow.
Is that something you can control? How many pieces of transaction can you make a transaction? But I guess it's about the data size. You can't about the total sum. Can you divide a big transaction into 2 smaller ones? If you think that transaction is likely to cause trouble for you, I don't know if that's possible.
this could be done, but extremely hard in a hardware level. So maybe software, because only programmers know about what their transaction is all about.
Could the program be written considering that this is the underlying architecture?
Yeah, so there's an old research in HE Lab that say, we have a new design, we should force programmers to leverage our design with smaller transactions. But the thing is that the programmers, they're like maybe sort of lazy. If another company or another people provide a better implementation, I don't need to change any more program. So that one is, that's one more competitive.
Yeah, so can we just follow Intel's strategy? That is, just provide just as good transaction memory support. So if it's too large, I just abort, and then the program needs to actually.
That's the hardware transaction memory has well.
Mm-hmm.
Yeah, you can. So if we detect this one overflow, I can just give up with my hands. You to deal with whatever. But again, if I'm a user, I want a better solution than that. Of course, we can do that. But I don't know how. What do you think about Intel's Haswell processors usage? Because recently I met Dr. Lai he just retired from Intel. He said hardware transaction memory went into a kind of embarrassing situation. Not a lot of users actually using that part. So they're trying to find a killer application for that, but it's very hard. For persistent memory, I think at the same thing, killer application and also the memory device support is the two challenges for its widely adoption.
Right, let's take our
Thank you very much.